Hello everyone, my name is Shymik, and today I'll be presenting our project titled Pick and Place Automation with the U Factory Like 6. This work was completed under the guidance of Dr. K and Dr. Baek in the Department of Computer Science at Winston-Salem State University. To begin, I'll walk you through our overview of what we'll be covering today. We'll begin by introducing collaborative robot arms, then look at general characteristics and trade-offs observed in modern cobots. And from there, I'll explain the shortcomings we discovered in the currently available Light 6, which became the motivation from our project. Next, I'll present our proposed improved Light 6, including the pick-and-place pipeline, reliability improvements, self-collision recovery, motion planning, and impact. Finally, I'll discuss gripper improvements, implementation details, validation results, and future enhancements. Introducing collaborative robot arms. This slide introduces collaborative robot arms, also known as cobots. Cobots are robots designed to safely work with humans in shared environments. They're used widely across industries, in manufacturing and assembly for welding and packaging, in healthcare for surgical assistance and rehabilitation, in logistics for sorting and warehouse automation, and in education or research for teaching robotics and prototyping. A key point to note is that task complexity ranges from very simple pick-and-place actions to extremely high-precision tasks such as surgical procedures. This project particularly focuses on improving the U Factory Light 6 so it can become more reliable, safer, and better suited for everyday automated tasks. Next, to frame our motivation, let's look at the general characteristics observed in cobots. When evaluating cobots, we quickly notice there are trade-offs. High-end cobots are extremely advanced and capable, but they come with very high costs. On the other hand, low-cost cobots like the Light 6 are far more accessible, especially in educational settings, but they have limitations in precision, robustness, and reliability. So the ongoing challenge in robotics is balancing cost, complexity, and reliability. This trade-off is exactly what drove us to evaluate the Light 6 more closely. With this context in mind, let's move to the next slide. Observable common shortcomings in the Light 6 are motivation. During our work with the Light 6, we identified three major shortcomings. First, inconsistent gripper control. Different hardware versions of the Light 6 use different communication protocols, which resulted in unreliable opening and closing. Second, self-collision stops. When the Light 6 detects internal joint collisions, it enters a stop state and becomes stuck until manually reset. Third, was naive motion planning. The original Light 6 motions sometimes risk collisions with objects or table because they didn't follow a safe height strategy. These shortcomings motivated us to design an improved Light 6 with reliable gripper behavior and autonomous collision recovery. With the motivation being established, let's move to our next section, our proposed U Factory Light 6 pick and place pipeline. So, as you're looking at this slide, it actually shows the full pipeline we designed for the improved Light 6. It integrates gripper input-output control, object gripping, lifting object, safe motion planning, object placement, and collision recovery. This pipeline forms the core of the upgraded Light 6 pick and place capabilities. Okay, now Let's take a closer look at the reliability improvements. In this next slide, our improved U Factory Like 6 reliability. This slide highlights the three core improvements that make the enhanced Light 6 reliable. First, the gripper control using the input and output based actuation, which you will see in the pictures here. This ensures the gripper behaves consistently across all Light 6 models. Second, we have self-collision recovery through an incremental joint unfolding routine until the robot reaches a safe neutral position. Third, a conservative motion planning where the robot always ascends first, moves horizontally, and descends last. This prevents collisions with the table or obstacles. These improvements dramatically increase the reliability of the Light 6. Let's now explore individual improvement, beginning with self-collision recovery. In this slide, we detail how the improvement of the U Factory Light 6 handles self-collision recovery. The robot temporarily reduces collision sensitivity, then moves the joints into small 2-degree increments. It prioritizes adjustments starting from the wrist, then the elbow, shoulder, and base. This approach ensures the robot clears space around the effector first. The system continues until it automatically reaches a safe neutral pole. If any movement triggers a collision error, it retries the step after clearing the warning. This creates a fully autonomous recovery system. Following recovery, safe movement is essential. So let's move on to our improved motion planning. Our improved motion planning strategy ensures the robot navigates safely within its environment. It always begins with the vertical ascent, moves horizontally at a safe height, and finishes with the controlled descent. This prevents collisions with the table or surrounding objects and ensures predictable, smooth motion. Our improved U Factory Like 6 impact. This slide shows the impact of the improvements we made in the U Factory Like 6, and I also have a demonstration. Here you'll see the robot complete a full pick and place cycle smoothly, safely, and without any human intervention. You'll see that the robot's motion is stable and predictable. It also doesn't drag across the table or come close to colliding with surrounding objects. That's the result of the conservative motion planning strategy that we introduced. And here you can notice that the gripper reliably opens and closes using the input-output based control we implemented. This eliminates the inconsistent behavior seen in the original Light 6. And most importantly, the robot is able to maintain this behavior across repeated trials because it can autonomously recover to a neutral pose after any self-collision event. This demonstration captures the overall impact of our improvements. A Light 6 that is more reliable, more autonomous, and much more suited for practical, educational, and unmanned kitchen applications. Features of the improved gripper control. Here I'll have a demo video for you guys. This shows the features of the upgraded gripper control. We use the digital input output application. The gripper opens the 0.8 second pulse and closes with a 1.2 second pulse. This approach is hardware agnostic, eliminating firmware mismatches and assuring a reliable grasp every time. So let's get into our implementation details. One of the main motivations for this project came from the practical issues we repeatedly experienced while using the UFactory Lite 6 in our own lab. First, the gripper behavior was highly inconsistent across different hardware versions. Sometimes the gripper would not close completely. Sometimes it would close too quickly, and occasionally it would not even respond at all. These inconsistencies made it very difficult to achieve repeatable, grasping performance, especially during experiments that required the robot to pick the same object multiple times. Second, the Light 6 had a tendency to fall into self-collision states. Once a collision was detected, the robot immediately froze and required a manual reset. This not only interrupted our workflow, but also created safety concerns because students had to approach the robot and physically reset the controller. Finally, the default motion planning strategy was quite naive. The robot often attempted linear movements without considering obstacles such as the table or nearby objects. As a result, it was common to see the Light 6 swing his elbow or wrist into unsafe zones, creating unnecessary risk. All of these issues had a direct impact on the repeatability and safety of our experiments, and they strongly motivated us to develop a more reliable and autonomous solution. In terms of implementation, we deliberately chose a design philosophy that prioritized safety, simplicity, and reproducibility. We selected Python together with the official XARM API because the combination provides a clean, transparent, and highly controllable interface. It also allows students and researchers to understand the full control stack without needing proprietary software. Our conservative Cartesian planner was chosen because we value safety over raw speed. By always enforcing an upward movement before horizontal travel and controlled descent, we dramatically reduce the chance of contacting the table or surrounding objects. The joint stepping routine for collision recovery is also based on the principle of minimal motion by unfolding the joints in small 2-degree increments, starting from the wrist and moving outward. We ensure that the robot returns to a neutral pose without introducing new collisions. Overall, these choices reflect our goal of building a system that is not only functional but also trustworthy and easy to maintain in an educational environment. So here for our conservative Cartesian motion planner safe workspace limits, you can see X is in the range from 0 to 300 and Y is from the range from negative 300 to 300, as you can see here on the visual, and Z is from the ranges 80 to 260. So on this slide, I'm presenting our validation and experimental results, which confirm the improved Light 6 is reliable, stable, and capable of performing autonomous pick-and-place tasks without failure. To evaluate the system, we designed a set of control experiments that tested every component we improved: the gripper, the motion, planner, and the collision recovery routine. First, we tested self-collision recovery. We intentionally folded the Light 6 and took a strain in unnatural positions, causing it to enter a stop state. In 20 out of 20 trials, the robot successfully recovered back to a safe, neutral posture using our joint stepping routine. What's important is that this happened without any human intervention, something the original U-Factory Light 6 could not do. Next, we validated the complete pick and place cycle. This is where the step-by-step visual on the sides come in. The robot begins in a neutral pose, which is consistent and safe. It moves into the pick position using the improved motion planner, and the gripper performs a reliable input-output base close and secures the object. The arm then performs a controlled vertical lift, creating the clearance above the table. After that, it moves horizontally across the workspace. It performs the precision placement at the target location, and finally, it returns to a pick-ready pose, ready to repeat the cycle. We ran 30 consecutive pick-and-place trials, and improved Light 6 achieved a 100% success rate. Not a single motion failure, collision, or dropped object occurred during these trials. We also determined the optimal grasping height. At 82 millimeters, the robot made perfect contact with the object, and any higher caused unreliable grasp. And any lower risk scraping the table. This validated the stability of our motion planning in real-world conditions. In terms of performance, the full cycle, including picking, lifting, transporting, placing, and returning, took about 12 seconds, which is acceptable for safe, conservative automation. More importantly, the system maintained consistent behavior over multiple sessions across several days. These results demonstrate that our improved U-Factory Light 6 is not only functional, but robust, repeatable, and fully capable of autonomous operation inside environments like labs, classrooms, and early unmanned kitchens. Future improvements. For future development, we plan to include telemetry sensors, vision-based grasping, and more dynamic motion planning. These features will allow the Light 6 to adapt to changing environments, identify objects visually, and plan paths more intelligently. This concludes my presentation on improving the pick-and-place automation using the U-Factory Light 6. Thank you all for your time, your attention, and your interest in this work. I've included a QR code on this slide. If you'd like to explore more details, access the project files, or connect with me or Dr. K or Dr. Baek for future collaboration, feel free to scan it. Once again, thank you, and I'm happy to take any questions that you may have.